So this here, oscillation of electric currents. I like to say oscillation of electric charges, really. Think again of this electron moving backwards and forwards with regular period, regular oscillation. Okay, so this is kind of a, thank you, a simple harmonic motion. This charged particle, and of course there's, in real life, there's many of these electrons moving back and forth. And at this point here, we have constant velocity just for a moment, no acceleration. And at the two ends, imagine this is like a conductor here. This long line here is some sort of a conductor. At the two ends where the charged particle turns around and comes back the other way, the acceleration is at a maximum. So maximum acceleration here, zero acceleration here, maximum acceleration here. And the acceleration is what we're interested in because accelerating charges create electric fields. And I'll say more than that. I'll say a vibrating charge or a charge with regular oscillation will create an oscillating electric field. And we know now that if we have an oscillating electric field, there's the electric field, in the same plane as the oscillating charges here. So what we have is the same device at the top here, but I've just oriented it so that it's in perspective, and so that I can show you that this conductor here, imagine it like an antenna on a radio. Okay, this thing, this AC line, has of course free electrons moving up and down it. And if I can get them to oscillate with a regular oscillation or a vibration, then I create a regularly oscillating electric field. Because of that regular oscillating electric field or changing electric field, I have a magnetic field which is changing at right angles to it. If I have an oscillating electric field and at right angles to it, an oscillating magnetic field, then I have electromagnetic radiation, which is self-propagating, which means that it essentially makes itself continue on, propagates itself. Yes. That's right. Yeah, so that's right. We're about to get to that. So if we have an oscillating electric field created by these oscillating electrons in an antenna, which is transmitting, if we put an antenna over here in the same orientation, then it's this electric field, this oscillating electric field here, will cause the electrons in that antenna to oscillate. And that's how we receive a signal. It's not in reverse. Actually, they oscillate at exactly the same frequency at exactly the same time. So you can imagine as this wave moves across, what you would see is this part of the wave is at this point, and then at the next moment, you could see it'd be at this point, then the next moment after that would be at that point, and then after that it starts to go down the other way. And it causes, can you see that? As if this were moving with speed v across this way, the electric field would pass through these points up to here, then it would turn around and come back, and so on and so forth. I'll show you it's not a YouTube, it's a cartoon of what's going on there in a second. We'll get to that. I'll just remove that for now. So accelerating charges create electric fields, and this regular oscillation will create an oscillating electric field, and a changing electric field will create a changing magnetic field. The E field and B for magnetism field are self-propagating. If they couldn't do this, then light wouldn't travel through space and we'd have huge problems. Think about that. Okay, if light didn't travel through a vacuum, there would immediately be huge problems. I've got a picture here somewhere. Oops, too far. This is the same. This is a similar picture to what I've drawn. I've just got to draw because it has no background. I've got to draw and fill a white box so I can paste it in there, make it a bit smaller. Oops. About the same size as that. I'll put it over there and we're all right. Maybe a bit smaller. What we've got here, imagine now, in the red is the electric field. So what they've done is they've turned it around so that it's in a different plane of polarization to what I said before. So I've got it in the horizontal plane, imagine, okay, the electric field, and the magnetic field in the vertical plane. In this orientation here, they've drawn the electric field in the vertical plane, changing electric field, and the arrows represent the electric field at that moment. So it's only that tall there, the magnitude of the electric field at these moments here. Okay? Instead of drawing a line, a sinusoidal line, they've drawn the arrows. Of course, wavelength lambda between two peaks or two troughs or two identical points on the wave is the wavelength. And because of this changing electric field, we have a changing magnetic field that kind of looks like a mirror to it, but at right angles to it exactly. And one other thing, the direction of propagation of this wave, of this electromagnetic wave, is at right angles to both the electric field and the magnetic field. Okay, I'll state that. I already said about the that the magnetic field and the electric field are at right angles to each other. Now I'll just state that the direction the direction of the velocity of the direction of the velocity of the electromagnetic um, wave is perpendicular to both the E field, whoops, the E field and the B field. Its velocity is equal to its frequency multiplied by its wavelength. And because we're talking about light, we'll say C is equal to F lambda, because all light travels at the same speed in a vacuum. If we put it through a different medium, as you know from refraction that it changes speed, if we put it through something where there is some matter, then it's going to change speed. From this, we can see that the frequency is inversely proportional to the wavelength. The higher the frequency, the lower the wavelength. The higher the wavelength, the lower the frequency. Okay. What am I going to say here? Any questions at this point? I know this idea, for some of these ideas, oscillating electric charges, accelerating electric charges, creating electric fields, and the changing electric fields creating magnetic fields at right angles to each other, at right angles to the direction of propagation of that wave, of that electromagnetic wave, is for some of you quite new. This is the form of all light. When we introduced this topic, we looked at radio waves, microwaves, infrared, visible light, UV, X-rays, gamma rays, cosmic rays. Very briefly, they all look exactly the same. They just have different wavelengths or different frequencies, essentially. It's the same stuff. Okay? And they're all caused by exactly the same thing. How do I make an EM wave? Yeah, all I've got to do is make charges oscillate. Usually electrons. I've got to make them accelerate. Oscillate and accelerate. And if I can do that, then I create an electric field that oscillates exactly the same as the frequency of the oscillating charges. So from that, how if you look at radio waves, how fast does that oscillation have to be? With what frequency does the oscillation have to be relative to other frequencies? Low, yeah. It does that oscillation can be quite low frequency. A big pardon, sorry. Of the, yeah, that's right, exactly. So if we if we cause these oscillations to be quite low frequency, we're going to have a long wavelength. You can see that, can't you? Considering that it moves at exactly the same speed, c all the time. It's always c. Picture this. The wave's being created at speed c. And if I oscillate these charges slowly, then the wavelength becomes very long. We'll do a calculation shortly in an example where I think the wavelength of a radio wave is about 400 meters. Yeah, it's quite long. And then if you look at, go right up to X-rays, and we have frequencies that are really fast. Gamma rays even faster, cosmic rays even faster again. Okay. Yes. Why is C always the same speed? Yeah. Just the answer to that question probably we don't know why it's 3 by 10 to the 8 meters per second. We just know that it is. As with a lot of things in physics, you're going to find that it just is. Yeah. It's not. Shh, please. It's not that it. I guess it's not that it just is. It's that we've taken the physical world and then we've described some laws to explain that physical world. The meaning behind it, we don't know. We just know the rules of that game, if you know what I mean. We can see the game and we can experience the game and we can describe the rules, but we can't really know what the game's all about. That's the best way to describe physics as it stands today. I think that was Richard Feynman said that. Okay. Um, and so we know that light travels at this speed. Of course, we've decided what meters is and we've decided what seconds are. So it's 3 by 10 to the 8 by our standard. Okay. And our wavelength is measured in meters. By our standard, we've said the meter is about this long. On some other planet, they might have said the meter is from here to the moon. Okay. So it's arbitrary. These numbers that we say are really, they don't mean anything. But as far as we know, all around the universe, light will travel at that same speed. It will cover that same distance in the same amount of time. Okay. Antenna theory is next. Actually, before I show you that, I'll show you this. There's a demonstration here. Here we have a transmitting antenna. We can wiggle the electron and create an electric field in the same plane as the wiggle of the electron. Okay, and I can get it to oscillate. And of course, if I stop it, that's traveling at speed c, that wave. Notice here the antenna on this is a receiving antenna. This is our house, and our house has electrons in its antenna as well. If I start that oscillation going, travels at speed c to our antenna and causes the electrons in our antenna to vibrate up and down with same, even though not the same amplitude, the same frequency and the same wavelength. Yeah, that's right. So these travel much faster than what we can see there. If they were traveling as fast as they actually do, we wouldn't see anything happening really. And so, or we'd just see a blur. But this uh, this wave here is causing these to oscillate, and it's got a signal associated with it. So if we change, if the radio station has a device in it that can cause these electrons to oscillate at different frequencies, they can send a signal, okay? If we can change that frequency over and over again, many times a second, we send enough information so that at this end, this person has a speaker connected to their radio, which is the receiver, and the speaker can play lots of notes every second, lots of different notes every second, and we perceive that as music. Okay. Oh, just the curve. This is the full field. This is a bit freaky. That's in, yeah. Okay, so yeah, don't worry about that. We're only going to look in 2 dimensions here. That's the electric field. Oh, notice the force on the electron is opposite its acceleration. Is opposite its direction. So it's down here. The force is backwards. Force is backwards. Force is back. Okay, so is its acceleration. Acceleration direction is opposite its direction of motion. Yes, we are only going to consider the electric field in 2 dimensions. It's too difficult to look at it in 3 dimensions at this stage, and so we just consider it in 2 dimensions. Actually, because we only look at this oscillation up and down this antenna here, this transmitting antenna, then the electric, if they actually only oscillated up and down, then we would only create an electric field in 2 dimensions anyway. Okay. In reality, this antenna here is 3-dimensional, and the oscillation will mostly be in that direction, but probably could be a little bit side to side as well. Yeah, but don't worry about that. We're only interested in this oscillation up and down. Yeah, have a look at what they do is they show the electric field here. Notice how the electric field created is in the same direction as the motion of the electron. Where the electron reaches its peak and turns around, that's where the electric field is at its greatest point. Okay? But if we look at the force, remember the force is proportional to the acceleration. I'll go back to force and acceleration. They're opposite, in the opposite direction. How do I get this electron to slow down? I apply force that way. How do I get it to slow down? I apply force that way. Okay? Electric field, same direction, oscillates at the same frequency and with the same magnitude as the oscillation of the electron. The red line is the force. The red line is the acceleration. The electric field is the green arrows. Yeah. Okay, we'll move on from this and we'll probably come back to it. Some students are expressing concern that they're not quite understanding this, and it is difficult. We'll go on, we'll describe some more antenna theory. Start with some antenna theory. This is not the application to this topic. The application is laser airborne depth sounders. But antennas is kind of the application that goes with this topic, I think. You've all seen these on your roof, maybe, or most of us would have digital ones now, but you've seen them on somebody's roof. This device here. It's actually, these lines are not one piece of stainless steel. They're broken in 2. Okay, so they've got one side is independent of the other side. Okay, and you'll all notice there's a cable that winds up or goes up the side of this this pole here that holds on to the antenna, and is connected to these these rods here, these stainless steel rods or aluminium rods. And what that is an RF receiver, a radio frequency receiver. This, this antenna here is designed as a conductor, and of course, being a conductor, it's got electric charges in it, which don't do anything unless we cause them to do something, okay? They're just going to sit there, not doing a whole lot. If I send in a wave, and we're only looking at the electric field here, in the same plane, actually I won't do that, I'll do this. In the same plane, so this is its direction, its velocity, moving towards that antenna. In this, the same plane as the stainless steel rod itself, this wave here will cause those electrons to start oscillating backwards and forwards. Okay. This is E, and we know that if this is light, then we have a magnetic field as well at right angles to it. But I'm not going to worry about that at the moment. Okay. There's a magnetic field at right angles. So in the vertical plane, if we look at the page, I'm going to take that away though, because that just confuses things. That magnetic field helps this electric field self-propagate. We're interested in this antenna theory, in this electric field, because the electric field is the one that causes these electrons to oscillate backwards and forwards. They oscillate backwards and forwards in the same plane as this oscillating electric field. If I were to send in a wave that looked like this, I'll draw it in white for electric field. In the vertical direction, okay, so in the vertical plane of the page that we're looking at, is that going to cause these electrons to oscillate, do you think? It won't, will it? No. It may cause them to oscillate up and down inside the small part of the wire there, right at that moment there, but it won't cause them to do this with a reasonable amplitude, okay? This is why we, in the old days, we used to have to adjust our antennas, okay? And it's the reason why you might notice in the country, city radio stations in South Australia and all in all states, everywhere around the world, city radio stations will have their the orientation of their aerials or their antennas maybe horizontal, and whatever it is in the city, the country radio stations will have it oriented exactly opposite the plane, so perpendicular to that, so in the vertical. So this, we might call this a city antenna. You would see a country antenna that looked like this. Why? Why would you do that? It's not that hard. An idea, antenna, country antenna. Well, here's my city signal, okay? Causes my city antenna to receive that signal. If I've of course, because city and country is, it's not a perfect line that says this is city and this is country. I want these people to receive city information, city electric fields, and I want the country people to receive different electric fields. What we do is we say, well, city electric fields, the transmitting signal from the radio station, for instance, or the TV station, is oriented horizontal. So the city antennas receive that. And the country radio stations would be transmitting vertical. So the country antennas would receive that. You're not going to receive both signals at the same time, causing all sorts of problems, okay? And so we don't get this overlap of signals arriving at country aerials and city aerials. Some people in the country actually have, they have this antenna and then they have another antenna and then they have funny antennas like oh, no, they're, in the country, they've got all sorts of things going on top of these poles, and that's because they want to receive. They want to receive the country radio stations, and they want to receive the city radio stations, and they want to receive something else. Okay, so it gets quite complicated. I knew somebody that in Mount Gambier, which is kind of between Melbourne and Adelaide, round about halfway, not quite, but they probably a little bit closer to Melbourne. They used to be able to receive the Melbourne TV stations and also WIN, which was the country radio channel 9, I think it was, yeah, country radio station. So they had a whole load of stations that they could choose from, yeah. A big pardon? Ah, right, okay, yeah, so, okay, we have a city antenna and we have, this is one radio station, of course, here, isn't it? Um, what about different radio stations? This one's an easy one too, if you think about it. How do you change radio station? Yeah, you change the frequency of the receiving this device. Now, we might have an antenna. We might have an antenna here, and it's going to receive all signals, and we might have a different frequency. Whoops. Yeah, not that frequency. We might have a different frequency here that we want to receive also. These are all out there, of course. It's the device that's connected down here, the old radio, okay? And actually, this is its antenna here, isn't it? So, okay, so this is the old style radio. This device here has something in it where if we turn if we turn that knob, the receiver will receive certain frequencies only. Okay. Yeah, so that's why we change it. 107.1 in Adelaide, 107.1 million megahertz. Okay. Is it kilohertz? Yeah, AM and FM. Uh, yeah, I know what the M stands for modulation, and I don't know a lot about them actually. Yeah, to tell you the truth, but they are completely different frequencies. I just like you to know that. So if we yeah, so we know that in South Australia it's 107.1. I thought it was megahertz. It might be kilohertz. That's okay. AM's megahertz. AM is kilohertz. Yeah, megahertz. Okay, so million hertz. M HZ. Okay, and then we've got other radio stations. 104.7. Okay, yeah, megahertz. Now, if you turn this dial on the radio only receives signals that have that frequency. So we're sitting in all the frequencies at the moment. We're being awash everywhere. They're everywhere here at the moment. But it's only if you tune the radio, the receiving this device that receives that signal, it will receive this very specific signal only, or this very specific signal only. Yes. Yeah, that's right. So imagine if you changed it so that this oscillation here isn't in time with the oscillation that this thing is expecting. Then you're not going to quite get a very good signal, and that's when we get static and that sort of thing. All right. Yes. Yes. Oh, I don't understand when you do that. Oh, chuck a coat hanger on. Coat hanger is just made of is a conductor as well. It's made of I think they're made of steel. Yep. And essentially, if you can put a piece of steel into the old aerial slot, so the aerial broke off, and all you have is a little stub there with a little bit of metal on it. Of course, any signal that comes in isn't going to be able to oscillate electrons with a big enough amplitude. And so what you do is you stick a coat hanger in it, and that makes it so that the electrons can oscillate with greater amplitude. Okay? So imagine this. Okay, the aerial on this guy's broken, and so I stick in a coat hanger and then orient it so that the electrons in the coat hanger can oscillate backwards and forwards with big enough amplitude that this receiver here can understand it. Is that what you mean? That's why that works. Old cars, people used to put them on cars. Yeah, I haven't seen one for a long time, but yes, it does. Yeah, and well, what we're really interested in is we're interested in, as long as possible, a piece of metal, a conductor, oriented exactly the same plane so that it receives this signal. Okay. Yeah, that's right. Yeah, but sometimes that's sufficient. The spots on the so there's some people that make the Australian shape. Yeah, shape of Australia. I've seen that. If it works, it works. Some of the frequencies and wavelengths of these electric fields are sufficient. They only have to be very small oscillations, and this device can understand it. Okay. Okay. So transmitting the signal. Change colour. How much time do we have, people? Yeah, what? 15 minutes, thank you. We might do this next lesson, and I'll show you a video, because we've probably done enough theory for now. Transmitting the signal. Oh yeah, I did say before, think of each of the metal rods as one half of a dipole. Okay, so remember I said that this side is one half of the dipole, and this side here is one half of the dipole. They are not necessarily connected. And we'll go on with that next lesson.